Am I audible?
Yes, sir.
Yes, sir.
Okay. So what we'll do is today we'll discuss about electromagnetic potentials and gauge. Earlier in the electromagnetics course, we have studied these things. So I'll not go into details of this, just a revision of what we have studied in electromagnetics about electromagnetic potentials and Gauss transform. So that is what we are going to do. So let us start with a flashback of what we have learned earlier. So if I have a vector A, then the dot product of vector A with itself gives you the magnitude of the vector A. Cross product of vector A with itself gives you 0. So that is from vector analysis or basic vector theory that we know. Then we know the delta operator del is equal to x cap dou by dou x plus y cap dou by dou y plus g cap dou by dou g. Here I am writing dou x dou y dou z to represent either dou by dou x, dou by dou y or dou by dou z. So that is the notation that I am using here. So dou x is equal to dou by dou x. Similarly, dou square x is equal to dou square by dou x square. And dou t is equal to dou by dou t square is equal to dou square by dou t square. These are the expressions that we'll use. Then in the spherical coordinate system, the delta operator is equal to r cap dou r plus theta cap by r dou theta plus phi cap by r sin theta dou phi. So this is in the spherical coordinate system. That also then del dot del is equal to del square, because a dot a is equal to a square, or uh, so therefore del dot del is equal to del square, that is nabla operator, which is equal to dou x square plus dou y square plus dou g square. And expression for del square in spherical coordinate system is del square is equal to 1 by r square dou r square dou r plus 1 by r square sin theta dou theta sin theta dou theta plus 1 by r square sin square theta dou square phi. Del cross del is equal to 0. These are the things that we already know from vector analysis. Okay, then we know about the coordinate system. Next. 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 And then we know about the coordinate system. The Cartesian coordinate system is xyz, and the spherical coordinate system is r theta phi. And let us see how we can relate these coordinate systems xyz with r theta phi. You can see this figure. In this figure we are showing x-axis, y-axis and z-axis. Then we see a point P which is at a distance r from the origin, and if you join a vector from the origin to the point P, which is vector r, which gives the position vector of the point P, and that vector makes an angle theta with the z-axis, that is the theta component in the spherical coordinate system. Now from that point P, if you drop a perpendicular onto the xy plane, then the length of the perpendicular will be, because that perpendicular will be parallel to the z-axis, so that perpendicular will make angle theta with the r vector. Since that perpendicular will make angle theta with the r vector, the length of that perpendicular will be r sin theta, sorry, r cos theta. Now if that length is equal to r cos theta, which means from the xy plane to the point P, the distance, vertical distance from xy plane to the point P will be r cos theta. Then the point where it meets the xy plane, the perpendicular, where the perpendicular meets the xy plane, so that to that point, if you connect the uh, origin, So that length will be, you get a triangle in which angle theta is between r and the perpendicular dropped from the point P, and the line which is joining on the xy plane to the meeting point of the perpendicular, that line length will be r sin theta. R cos theta is vertical distance, r sin theta is the distance on the horizontal plane xy plane to the point where the perpendicular from point P meets the xy plane. So that will be r sin theta. Now from that point where you have r sin theta, that length, so from that point, if you drop a perpendicular onto the xy plane, onto the x-axis and a perpendicular to the y-axis, and you say that the angle between the x-axis towards y-axis, if you move from x-axis towards y-axis, the angle of the line connecting the perpendicular on the xy plane, that angle is phi, then the perpendicular from that point onto the xy x-axis will be uh, 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 onto the x-axis, that will be, so you have a perpendicular, this is length, so that will be r sin theta cos phi. Similarly, the perpendicular onto the y-axis will be r sin theta sin phi. Similarly, around the point P, if you take a infinitesimally small box, the square, this cube, small cubic box, then the length of that box, one side of the length of the box will be along the r axis. If you extend it infinitesimally small, therefore along r axis it will be dr. Now along the theta direction, so it will be r d theta, and along the phi direction it will be r sin theta d phi. So these will be the three sides of the box, lengths of the three sides of the box. One is dr, other is r d theta, and the final one along the phi axis will be r sin theta d phi. Therefore, the volume of the box will be r square and r square sin theta d phi dr. That will be the volume of the box. Okay. Now delta dot is equal to this. We have seen 1 by r square dou r square plus 1 by r sin theta dou theta sin theta plus 1 by r sin theta dou phi operating on something. So then delta cross A will be the curl. The curl will be delta cross A will be r cap by r square sin theta. In the first row, it will be the determinant of a 3 by 3 matrix. The first row of that matrix will be r cap by r square sin theta, theta cap by r sin theta, phi cap by r. Second row will be dou r, dou theta, dou phi. And the third row will be ar, r a theta, r sin theta, a phi. This is what we know. Already these are the mathematical preliminaries, vector preliminaries that we know, and the preliminary on the coordinate system, that also we know. So with this preliminary background, let us move to a typical radiation problem. In the typical radiation problem, a typical character is there will be the Maxwell's equation will radiation problem is dealt with Maxwell's equation, and the two core equations are basically responsible for radiation, and each of these core equations, they contain both the fields, electric field and magnetic fields. These two core equations are coupled to each other, and since they are coupled to each other and they contain electric field and magnetic field, therefore they need a simultaneous solution. These core equations need to be solved simultaneously, and solving a coupled equation, particularly in the differential form, when they are in differential form, solving a coupled differential coupled line of coupled differential equations is a very difficult task. So simultaneous solution for E and H from the Corl equation is a very difficult task. So, so the solution that requires that we should have some approach, some convenient approach, which is an alternative approach. Instead of solving for E and H, electric field and magnetic field, we will solve from some other thing, some other entity, and from that entity we will find out E and H. So E and H, what we will do is we will find out E and H appropriately in terms of some other entities, and we will find out the solution for those entities. Then from those entities, by the relation to E and H, we will solve for E and H. So you require an alternative approach. In the alternative approach, what we do is we judicially choose vector identities and convert the Corl equations to uncoupled wave equations. Once you convert the Corl equations to uncoupled wave equations, then you can solve those wave equations, and from that solution you can find out what is E and H. Okay. Now you know from the discussion on antennas, we have started why antenna radiates. From that we know if we have a impressed current distribution, particularly impressed current distribution, when we say it is AC, alternating current distribution. So if you impress some alternating current onto a metal or onto a dielectric, whatever it is. So once you impress a current, so because of the current distribution, that creates electric field and magnetic field. So the source of electric field and magnetic field is an impressed current distribution or accelerating charge. Now, and the field distributions, they come from the Maxwell's Corl equations. Corl H is equal to J plus and dou T D, and Corl E is equal to minus dou T B. These are differential equations, these are first order equations, and these are two linear first order equations. And solving them is difficult. Why we have discussed that, why solving these two equations are difficult, and why we require a alternative approach to solve these equations. Next. So to solve them, we have find out something called electromagnetic potentials. So to find out electromagnetic potentials, we will use some useful vector identities. For example, A dot B cross C is equal to A cross B dot C. That is one identity that we are going to use. Then if in this identity we take A is equal to delta and C is equal to a vector small a, B is equal to vector delta, then A dot B cross C is same as del dot del cross A. So that will be equal to, from the identity we know A dot B cross C is equal to A cross B dot C. So del dot A del cross A is equal to del cross del dot A. Del cross del is equal to 0, so that will be 0. So del dot del cross A is equal to 0. This is one identity on the del operator that will use. That is, this is one identity. Then suppose we have two vectors k and l, and their cross product is another vector m. So k cross l is equal to m. And now for k, let us take del. For l, let us take a vector a, and for m, let us take another vector u. So del cross a is equal to u. Now del cross a is equal to u. From that we will find del dot u. If I take divergence of that equation on both the sides, del cross a is equal to u, take divergence on both the sides. So then del dot u, or divergence of u, is equal to divergence of del cross a. Then we know the identity is del dot del cross a is equal to 0. So del dot del cross a will be 0, divergence of u will be 0. So k cross l is equal to m. From that, when we use del cross a is equal to u, if curl of a vector is another vector, then the divergence of the resulting vector is always 0. So if you can express a vector as the curl of another vector, then the divergence of that vector is always 0. So that is one identity. Then A cross AG, G is a scalar, A cross AG is equal to A cross A into G, that is equal to 0. So this is one identity. Now let us take A as del. So del cross del G. So curl of grad of G is equal to 0. So this gives us curl of grad of G is equal to 0. Now let us try to apply these identities. We have seen some identities. Then let us see the application of these identities. Now in Maxwell's equation we know divergence of B is equal to 0 and B is equal to mu H. So let us take, since divergence of B is equal to 0, and we have seen that if divergence of a vector is equal to 0, then that vector can be represented as the curl of another vector. So we can write B, which is equal to mu H, as curl of another vector. So let us write B is equal to mu H is equal to curl A. So A is some other vector, and B is related to A by this relation. B is equal to del cross A, or mu H is equal to del cross A. Then we know curl of E is equal to minus dou B by dou T. That we know. Now curl of B is equal to minus dou T. Then for B we can write curl A. Now dou T is a differential operator on time. So this is differentiation with time, and curl is differentiation with space. So since time and space are independent upon each other, so these two operations, time operation and space operations, can be interchanged. So dou T del cross dou TB, that also you can write as curl of dou T A. So that way we can write. So curl of E is equal to minus del cross dou T A. Now take everything to the left side. So that gives us curl of E plus curl of dou T A is equal to 0, from which we find curl of E plus dou T A is equal to 0. Now if we have seen curl of grad G is equal to 0. So curl of E plus dou TA is equal to 0. So from that we can say E plus dou TA can be expressed as the grad of some other function. So we can write E plus dou TA is equal to grad of phi, minus grad of phi. You can write this grad as phi, but for a specific reason we are taking it as minus grad phi, and the reason will be clear later. So E plus dou TA is equal to minus grad phi. This is what we have got now. We have got two equations. One is B, which is equal to mu H is equal to del cross A. So instead of B we are going to use del cross A. Similarly for E we have got E plus dou T is equal to minus grad phi, or E is equal to minus grad phi minus dou TA. So that we will get, that is what we are going to use for E and B. Instead of using E and B in the Maxwell's equation, we will use curl A and minus grad phi minus dou TA. That is what we are going to use. Next. Next. Okay, these are the two equations that we are going to use. And we know mu H is equal to curl A. That shows that H is equal to 1 by mu curl into curl A, which means divergence of H is also 0. Divergence of B is 0 and divergence of H is also 0. And divergence of H is 0 means H cannot diverge out, so there is no open fields from H. There is no open loop of magnetic field. Always H has circulation or there are closed loops. Okay. So this is, if there is only circulation, this type of field is called a solenoidal field. So H is a solenoidal field. It possesses only circulation, that as I told you. So it can be represented by curl of some other vector function A. H can be represented as curl of some other vector function A that we have seen. Now this A is called the magnetic vector potential. When mu H is equal to curl of A, we call this A as magnetic vector potential. And divergence, now what is important is that A is a vector and its curl gives you mu H. Then to represent a vector completely, you need to know what is the curl of that vector and what is the divergence of that vector. We know, for complete definition, we know these two. We require these two things: curl of the vector and divergence of the vector. Curl of the vector we know mu H. Then divergence of the vector is unknown. Del dot A, what is del dot A? That we do not know. Del dot H is equal to 0, but what is del dot A? We do not know. So there can be del dot A can be anything, which means we can have different del dot A. So different values of H. So same value of H for different values of A. So divergence need to be specified for complete definition of A. We have only the curl available to us. At this point, we have only the curl available to us. Next. So which means A is not unique and delta dot A next is unspecified, because divergence of A is unspecified. So A is not unique. But we know what that its curl is then E plus dou T A is equal to minus grad phi and its curl is equal to 0, that we know. So since its curl is equal to 0, we know this will be a conservative field. This type of field where curl is equal to 0, that gives us a conservative field. Dimensionally, both sides of this imply that it is an electric field. And then this behaves as a static electric field. That is why, and in the static electric field, you know E is equal to minus grad V. So that is why we have taken minus grad phi for this. So dimensionally, E plus dou T A is equal to minus grad phi. That gives an electric field, dimensional electric field. So dimension of the left side and dimension of the right side are the dimension of electric field. Therefore, it behaves like a static electric field. The constant phi, or the vector, the scalar phi is a scalar. So the scalar phi is called the electric scalar potential. Again, a grad phi is defined. So phi is not unique. Since A is not unique, and therefore phi is also not unique. Now what we have to do is we have to find out the unique values of A and phi. We have to somehow, otherwise how you will find the field? Unless A and phi are unique, how you are going to find the field? So we are going to find the unique values of A and phi. Now for that we use something called Gauss transformation. So since the potentials A and phi are not unique, we are going to use a Gauss transformation. Now, for example, let us see, you have A and phi. Change A and phi by adding a constant to them. So now let us, instead of A, let us write A dash is equal to A plus C, C is some vector, and phi dash is equal to phi plus K, K is some scalar. Then if A is equal to A dash plus C, then curl of A dash is equal to curl of A plus curl of C. C is a constant, therefore curl of C is equal to 0. So curl of A dash is equal to curl of A. Curl of A is equal to H. So H is equal to curl of A, H is equal to curl of A dash. So H you can find out from two vectors or n number of vectors, n number of such vectors. So instead of C, if you take C1, C2, C3, etc., there can be infinitely many vectors for which curl of that vector will give you H. So A is not unique. That is what we say. Similarly, for phi you can do the same thing. Change by adding the constant to them, and you require that gives us more freedom for possible values of A and phi. That gives us more freedom, which means we require a gauge variance of Maxwell's equation because there is more freedom. More freedom is possible in determining A and phi. We have gauge invariance of Maxwell's equation. What is meant by gauge invariance? Let us see that Maxwell's equations are invariant under gauge transform. That means gauge invariance of Maxwell's equation. It says that Maxwell's equations are invariant under gauge transform. Let us see what is this. Now consider some scalar function f rt, which is a function of space and time. R is space. So for any scalar function f r t, we will use the two Gauss transformation. Let us consider the two Gauss transformations. So the Gauss transformations are for phi. Let us take phi dash is equal to phi minus dou tf, that is one Gauss transformation, and a dash is equal to a plus grad f. F is a scalar function. So phi dash is equal to phi minus dou tf. Phi is scalar and dou t is also scalar. So dou t operating on a scalar function f gives you a scalar. So phi dash is also a scalar. Phi is scalar, phi dash is a scalar. Now a dash is equal to a dash is a vector. Now whether we'll find out a dash is a vector or not, let us see. A is a vector. To that we are adding grad of f. Grad of f is a scalar, but grad of a scalar function is a vector. Therefore, A is a vector plus grad of f, which is another vector. So addition of two vectors will give you another vector. So A dash is also a vector. So phi dash and A dash are two vectors. Now, if you take these two vectors, you find out E and B from phi and A, and we find out E and B from phi and A, and find out E and B from phi dash and A dash. Both these will be same. That is what we are going to see. So next, so we are starting with this, that A and phi are non-specific. E dash is equal to minus dou t A dash minus grad phi dash, that we know. So that implies that E dash is equal to minus dou t. For A dash we can write A plus grad phi, as we have defined what is A dash. A dash we have defined as A plus grad phi. Similarly, phi dash we have defined as phi minus dou tf. Therefore, E dash will be equal to dou t A plus grad phi minus grad of phi minus dou tf. How you got this? The simple answer is, we have already seen E is equal to minus dou Ta minus grad phi. So following the analogy, we can write E dash is equal to minus dou Ta dash minus grad phi dash. So we used that. Then we used for A dash we used A plus grad phi. For phi dash we used phi minus dou Tf. Now look at the right hand side. Right hand side is dou T operating on A plus grad F minus grad phi minus dou Tf. So if we look at that, the first term is, the third term is minus grad phi. So let us take that first, minus grad phi. Then and dot minus dot Ta. So we put minus dot Ta. Then we have delta and grad of dot Tf minus into minus grad of minus dot Ta, that is plus. So plus grad of dot Tf minus dot T of grad f. And as we know, grad and dou t, this grad is a function on space, whereas dou t is a operation on time. So space and time operations can be interchanged because they are independent, completely independent upon each other. So grad of and dou t of grad f and grad of dou tf both are same. So grad of dou tf and dou t of grad f are same. So grad of dou tf minus dou t grad f, that will be equal to 0. They will cancel with each other. So therefore E dash is equal to minus grad phi minus dou Ta, and we know E is equal to minus grad phi minus dou Ta. Therefore E dash is equal to E. So under the transformation that we considered, back back हाँ, back करो back करो ना हाँ हेलो हाँ ओहो आओ back करो नहीं अबे forward करो next 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 so we have the freedom of selecting potentials that we saw now. We have the freedom of selecting potential. So E is equal to minus grad phi minus dou Ta, and E dash is equal to minus dou Ta dash minus grad phi dash, what E is equal to E dash. Therefore, we have the freedom of selecting the potentials A and phi. If we take A and phi, or we take A plus grad phi, grad f, and phi minus dou tf, it is immaterial. We have got the freedom of selecting the potentials. So imposing, since we have got the freedom, we will use this freedom judiciously by imposing some convenient constraints between the constraint means some convenient restrictions. So if we put some convenient restrictions between them, so we are now free to use any restriction that we want, because we are free to choose f, and we are free to choose grad f, we are free to choose grad phi, and so we are now free, we have the freedom of choosing them. Therefore, imposing some convenient constraint between the potentials, we can find out the electric fields properly. Next. Next. Now, on the knowledge of potential functions A and phi, that gives us the fields E and H. Complete expression for E and H can be obtained from the knowledge of potentials A and phi. We know mu H is equal to curl A, that is 1. So from that we can write H is equal to 1 by mu into curl A. Now from that we can write curl of H, if I take curl of both the sides, curl of H is equal to 1 by mu curl of A, but we know curl of H is equal to J plus dou dt. So 1 by mu curl of H is equal to J plus dou dt. Now let us use the back-cab rule, the vector identity. For curl of A, we'll use the back-cab rule. If we use the back-cab rule, next, we'll get curl H is equal to 1 by mu curl of A, that is gradient of divergence A minus del square A. So and that is curl of H is equal to J plus dou dt. So that is equal to J plus dou dt. Now from that we can write J plus dou dt is equal to that we know J plus dou dt, d is equal to epsilon E. Epsilon is constant, permittivity is constant, we are considering isotropic medium, so permittivity is constant. So J plus dou dt is equal to J plus epsilon dou dt. So for that you can take J plus epsilon dou t operating on E. E is equal to minus dou Ta minus grad phi. So write that. So then you expand that. So that will be j minus epsilon dou t square a minus epsilon dou t grad phi. Okay. So from that we can say grad of divergence A minus del square A is equal to mu J plus mu dou dt, and that we know. From that put mu J plus, for the right hand side you put mu J, then minus mu into dou dt. For dou dt we have found out what is J plus on dou dt, that is j minus epsilon dou t square a minus epsilon dou t grad phi. So write that mu j minus mu epsilon dou square t a minus mu epsilon dou t grad phi. And you know mu epsilon is equal to 1 by c square. So put that. If we put that, then this becomes, right hand side becomes mu j minus 1 by c square dou t square a minus 1 by c square dou t grad phi. So from that, if I take except mu j, if I take everything to the left side, then that becomes del square a minus grad of divergence of a minus 1 by c square dou t square a minus 1 by c square dou t grad phi is equal to minus mu j. Now left hand side of this equation is purely potentials, electric potential, vector potential, sorry, yes, vector potential and scalar potential. So A and phi. At the right hand side is the source current J, mu J. So the source, this indicates that the source is resulting in some potential, and potentials are resulting in field. From potentials we can find field. So now we know that if we have a source, and this source can generate potential, or in other words source can generate field, because potentials are related to field, or fields can be obtained from potentials. Now on the left hand side, if I take two terms each, del square a minus 1 by c square dou square t a and minus gradient of divergence a plus 1 by c square dou t grad phi, that is on the left hand side we take two terms, that is equal to minus mu j. Now the first term, which is del square a minus 1 by c square dou square t a, that is an equation which we have already seen in the wave equation. So this is the left hand side of a wave equation. If you look at a wave equation, it is del square a minus 1 by c square dou square t a, and the second term, which is grad of divergence of a plus 1 by c square, 1 by c square dou t phi, this second term is independent upon the first term. So these two terms added gives us minus mu j. Now let us try to specify a. What will be a? Next. So let us try from these two terms, let us try specifying a. So we'll try to specify divergence of a, therefore we'll find out what is a. Now let us consider the wave equation. It is del square a minus 1 by c square dou square t a, and on the right hand side let us consider the mu j term as it is. So the second term we are not considering. This is the wave equation. We say that j is giving us a. So from j we are getting the potential. But we also have from the wave from the equation already we have got del square a minus 1 by c square dou square t a minus gradient of divergence of a plus 1 by c square dou t phi is equal to minus mu j. Now if we want to get the wave equation from this equation, then the portion in red, which is gradient of divergence of a plus 1 by c square dou t phi, should be equal to 0. So I will use this condition. Condition to get the wave equation is divergence of a plus 1 by c square dou t phi is equal to 0. Under that condition we will get on the wave equation. This condition is called the Lorenz equation, because L Lorenz, remember that it is not H Lorenz from which you know the Lorenz contraction, etc. So that is not the Lorenz, not that Lorenz. It is Lorenz. L. Lorenz. He used this condition. That is why it is called the Lorenz-Gauss condition. So this condition is given on A and phi. So the Lorenz-Gauss condition gives us grad of divergence of A plus 1 by c square dot T phi is equal to 0. This is the Lorenz-Gauss condition. Now why this is done? This gives us because we have the freedom of choosing A and phi. So we choose A and phi in such a manner that on divergence of A plus 1 by c square dot T phi is equal to 0. So you under this condition the value of A is unique and the value of phi is unique. Value means the function A becomes unique, function phi becomes unique under this condition. And our function A obeys the wave equation del square A minus 1 by c square dot T square A is equal to minus mu j. Now we will see what is function phi, whether function phi obeys such condition or not. This condition is also called the radiation Gauss condition because this is the condition based on which we get the potentials, and the potentials gives us the fields, and these fields are the radiated fields. That is why it is called the radiation Gauss condition. Next. And now suppose they do not satisfy the constant divergence of A plus 1 by c square dot T phi is equal to 0. If this is not satisfied, then A and phi will not be unique. Now we'll see that if this is satisfied, then A and phi are unique. A is unique, that we have seen. Now on transform potentials A and phi, let us consider the transform potential A and C. How to proceed for that? Use the Gauss transformation. The transformation is phi dash is equal to phi minus dot Tf, A dash is equal to A plus grad f. Use that in the condition del divergence of A plus 1 by c square dot T phi is equal to 0. So if you use that, then that becomes on del divergence of A dash plus 1 by c square dot T phi dash. That will be equal to, for A dash will use the for A dash you write grad divergence of A plus 1 by c square dot T phi minus 1 by c square dot square Tf minus del square f. So this is what we get using the Gauss transformation for A dash and phi dash. Once we use this, then for A dash and phi dash we get divergence of A plus 1 by c square and dot T phi minus 1 by c square dot square Tf minus del square phi. Now we need appropriate choice of the function f. So f to be solution of the inhomogeneous wave equation, which is f has to be the solution of inhomogeneous wave equation, we need divergence of A plus 1 by c square dot T phi, that is equal to 0, and divergence of A plus 1 by c square dot T phi from the above equation is equal to 1 by c square dot square Tf minus del square f, because del dot A dash plus 1 by c square dot T phi dash is equal to 0. Use that condition, that is equal to 0 gives us divergence of A plus 1 by c square dot T phi is equal to 1 by c square and dot T square f minus del square f is equal to 0. And now from this, using this, okay, next. Using this, we will find out what is E. 1 by epsilon rho is equal to divergence of E, that you know. Divergence of D is equal to rho, D is equal to epsilon E. Therefore, divergence of E is equal to rho by epsilon, or 1 by epsilon into rho. Then we know E is equal to, using the potentials, we write E is equal to minus grad phi minus dou Ta. And then we also know the Lorenz condition, divergence of A plus 1 by C square dou T phi is equal to 0. So these three we know. Now let us write what is del dot E, divergence of E. Divergence of E is equal to divergence of, for E we will write minus grad phi minus dou Ta. So divergence of minus grad phi minus dou Ta. So if I take the divergence inside, so divergence of divergence phi is equal to del square phi. So that gives us minus del square phi. Then minus dou T will keep outside, and divergence of A, divergence operating on A. So that will be inside. So minus dou T of divergence of A. That you can write as minus del square phi minus dou T of, since divergence of A, find out what is divergence of A. Divergence of A is equal to minus 1 by C square dou T phi. So put that. So that will be minus 1 by C square dou T phi. So that gives us 1 by C square dou square T phi minus del square phi. So E and divergence of E is equal to this. So next. So now we get del square phi is equal to 1 by C square dou square T phi minus 1 by epsilon rho. Then del square A is equal to 1 by C square dou square T A is equal to minus mu j. The two wave equations we got, one wave equation in A, one wave equation in phi. So now we know that in a Maxwell's equation, the two Maxwell's chord equation, using the two Maxwell's chord equation, also we get the wave equations in E and wave equations in H. Now from those two equations, these two equations are giving us wave equation in phi and wave equation in A, which means this expressing the potentials in expressing the potentials using the Gauss transformation gives us the potentials in the form of Maxwell's equation, equivalent form of Maxwell's equations. So instead of using the Maxwell's equation, we can use this A and phi. So these equations are inhomogeneous wave equation. Okay, next. The densities, the charge density rho and the current density J, they are the generating sources for the potential phi and A. So these are the source terms for potentials phi and A. And fields E and B, they can be expressed in terms of these potentials. Next. This we'll see in the next class because our time is up. So we'll stop here for today. We had a 1 hour class, so we'll stop here today. ये कुछ Chrome. बस बंद करो नहीं wait. So now मत कहला तमरा क्लास अच्छी कि नहीं यहाँ पर आज
No sé.